Hello everyone, this is Dr. Hopkins with our next video. Now we're going to do acid-base reactions, except now one of them are going to be weak, so weak acid and base reactions. So in our strong acid, strong base reactions we just did, they all go completely 100% to products, so they go to completion. So the question is, will it be the same if we have a weak acid or a weak base for that matter? So let's check this out. Let's see. So we're going to react a weak acid, acetic acid, with sodium hydroxide, which is just OH minus. We're going to drop the sodium because it doesn't really matter. Remember, it's a spectator ion. And so we have this equilibrium. We're going to check to see if we need to keep this as an equilibrium. So that equilibrium can be written as a combination of the Ka of acetic acid, so it's a weak acid, and the inverse of the autoionization of water, which I've written here. So then the equilibrium constant for that is 1 over Kw. And so you'll notice if you add these up and sum them, it sums to the equilibrium above, where the two H3O pluses are going to cancel. One of the H2Os are going to cancel, and we're left with that previous equilibrium. And we know that if we add equilibria together, we multiply the equilibrium constants. So that means that our K for that reaction would be Ka over Kw, which is going to be 1.8, in this case, 1.8 times 10 to the 9th. So it's going to be in the billions. It's a very large K. It means we're going to produce mostly or pretty much all products. And so you'll notice that's kind of a theme. Even though this was a weak acid, in a just like we had with the strong acid, strong base, it's the acid plus base reacting to form water. The K on that is very large. That drags what is not a very large equilibrium along to products. So we'll see that theme go throughout. If we're talking about a weak base, if we're adding acid plus base and we're making water, that equilibrium is so large that it tends to drag them along to products. So if we had that, we would write that equilibrium with an arrow, so there's no equilibrium at all. So it's just acid plus base gives us water and the salt in this case, or the acetate. And so now we have an arrow. That means we're going to have to start with the stoichiometry. We're going to have to do stoichiometry to do this reaction. That means figuring out moles of acetic acid, moles of OH minus. And then we need to figure out at the end, after we've reacted it, what's the strongest acid or base left, and that's going to dictate what's our pH or what happens. So why don't we do a problem where we're going to add 10 milliliters of 0.5 molar sodium hydroxide, our strong base, with 10 milliliters of our 0.5 molar acetic acid. Now here we have our problem set up. So we've got our acetic acid plus OH minus giving us water and the acetate. And now remember, we had 10 milliliters of 0.5 molar and 10 milliliters of 0.5 molar. So we've added to a total of 20 milliliters. Now we'll look and let's do the stoichiometry of this. And I've written it kind of like an ice table. It's not an ice table. We have to have moles. And so they're 1 to 1. So this is going to react. So we're going to have no limiting reactant at all. They're both stoichiometrically equivalent, so we'll end up with 0 of each of those. Doesn't really matter how much water we get, right? Because we don't factor that in. But you'll notice this acetate is, because in the strong acid, strong base, we only generated water. We ignored the spectator ion. Acetate is not a spectator ion. It's actually a base. So we would need to add the number of moles, and we have 5.0 times 10 to the minus 3 moles of acetate. So what's going to dictate our pH? And the choices are, because notice we have none of those left, it's H2O or C2H3O2 minus. So in other words, which one's going to be the stronger base? And it turns out that it's acetate, because that is the conjugate base of a weak acid. So we're left with 5 times 10 to the minus 3 moles of acetate. So let's figure out, because obviously now we're going to have to do an ice table. So let's figure out, so you got 5.0 times 10 to the minus 3 divided by 0.020 liters. And that's going to be our concentration of acetate. And then I think, if I'm not mistaken, that's 0.250 molar. Okay, so that's our initial concentration of acetate. We have a weak base problem. Okay, it's a weak base, and I would like to know the Kb. So the Kb is equal to Kw divided by Ka, right? Because this is the Ka of acetic acid, and then we want to figure out the Kb of acetate. So that's 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5, which is 5.6 to 2 significant digits times 10 to the minus 10th. That's our Kb. Okay, let's set up our equilibrium. So we have C2H3O2 minus. We also have water. We generated, it was always the solvent. Okay, so that's a Kb reaction. It's 5.6 times 10 to the minus 10. We're definitely not going to write that with an error. That's definitely an equilibrium. And then we're going to generate the conjugate acid, which is HC2H3O2 plus OH minus. And I've lost the symbols here, so those are both aqueous. Okay, so I don't have enough room. Now let's set up our ice table. So we would put our columns in here. So our initial concentration, now H2O, we're going to get rid of. Our initial concentration of acetate, after we've done our stoichiometry, our concentration is 0.250. We got rid of both of these. You'll notice this is not exact. This is like the reverse of what we just did, but this is a weak reaction. So we've got 0 of those at the beginning of this equilibrium. And then we do our algebra. So that's minus x, that's plus x, that's plus x. So it's 0.250 minus x, and then x and x. All right. And so then we write this out. I'm going to go ahead and be kind of complete here, where we have HC2H3O2, so our acid, and our base over our base, weak base. So these x's here. Now notice this is 10 to the minus 10. This is 10 to the minus 1. So we're going to drop the x. So we're going to assume it's small. I'm not going to write it anywhere else. And so this would be x squared over 0.25. And the Kb on that was 5.6 times 10 to the minus 10 equals x squared over 0.25. We have a quadratic that's fairly easy to solve, which I get x equals 1.18 times 10 to the minus 5. That's our OH minus concentration, and we convert that to a pH through POH, and we get 9.07. Notice it's basic. So if you remember when we got, so you'll know we added equal moles of acid and base originally when we did this problem. When we did that for strong acid, strong base, we were left with just water. The pH was 7. It was neutral. In this case, because we're generating a conjugate base, the pH is basic at the equivalence point where we have equal number of moles. Now we've done one where we had excess of, we've done one at the equivalence point. What if we had an excess of our strong base? What would the resulting pH be? So here we have the problem set up. We've got 15 milliliters of 0.5 molar OH minus, 10 milliliters of 0.5 molar acetate. I've got the reaction set up for our stoichiometry. Now we need to figure out what's limiting. So I put both of our moles here, 5.0 times 10 to the minus 3 is our acetic acid moles. 7.5 times 10 to the minus 3 is our OH minus moles. So I think the 5 is limiting. So that's going to remove all of that. And minus 5.0 times 10 to the minus 3. So we're going to be left with no acetic acid left. But we have 2.5 times 10 to the minus 3 moles of OH minus. We don't care about water. And then we are actually still adding 5 times 10 to the minus 3 moles of acetate. So 5.0 times 10 to the minus 3 moles there. So we're left with, so then the question is, we have two bases left. We have OH minus and we have acetate. Which one is going to be stronger? Which one's the strongest one left? Because the strongest base, or the strongest acid left, is going to dictate our POH, or pH, or POH for that matter. So OH minus is most definitely our stronger base because it's a strong base. So we just need to know the concentration of OH minus, which is 2.50 times 10 to the minus 3, and that's moles. And then the milliliters, we had 10 plus 15, so it's 25 milliliters. I'm going to convert that to liters without doing the extra math. And if we do that, we're left with 0.1 molar OH minus, which we can convert to a POH, which would be 1, and then the pH is equal to 13. So here we've reacted the reaction. We've reacted away all of the weak acid. We still have some weak base, but the weak base is not going to affect anything. And we could plug that back into an equilibrium and figure that out. But basically, the pH is dictated by OH minus. Because remember, even without the OH minus, the acetate gave us a pH somewhere around 9. So we're a much higher pH in this case. Now we've been through two possibilities, the equivalence point, excess strong base. Now let's go through what would happen if we were to have an excess of weak acid. So let's start with 5 milliliters of 0.5 molar sodium hydroxide mixed with 10 milliliters of 0.5 molar acetic acid. So we have excess acetic acid, but we're going to show this. Here we have the problem set up where we have our 10 milliliters of 0.5 molar acetic acid and our 5 milliliters of 0.5 molar hydroxide. I've got the reaction set up, our stoichiometric reaction. We have our number of moles initially. Now we have a different limiting reactant. So it's going to be the hydroxide that's going to be limiting. So this is going to be, this is going to be 2.5 times 10 to the minus 3. This is minus 2.5 times 10 to the minus 3. So we're left with 0, strong base, and we get 2.5 times 10 to the minus 3 acetate. All right, so we're left with acetic acid and acetate, each same number of moles. Now the question is always, what is the strongest acid or base left? And so here we look at what we have left. We have water. Okay, that's clearly not the strongest. We don't have any OH minus left. We have acetic acid, which is a weak acid. And we have acetate, which is a weak base. Now, we could choose, and if we went by K's, we would choose acetic acid. However, you have to notice something. This is an acid conjugate base pair. So they go together. So if we're going to use one, we have to use both. So both will control our pH in this case. And so what that means is we would set up an equilibrium. So we have, and I'm going to go ahead and set up the Ka equilibrium because that's easier, plus H2O liquid And then that's in equilibrium with H3O plus. Notice that's easier because we actually get H3O plus as one of our products. And this is C2H3O2 minus. Sorry, I don't have any room. Now, so if we were to set up our ice table in this case, our initial concentration of H3O plus is 0. Our initial concentration of acetic acid is the 2.5 times 10 to the minus 3 divided by, what do we have, 15 milliliters. So if I'm not mistaken, that's 0.167. And then we have the same number of moles of acetate, so that would be 0.167. We would have minus x, so it would be 0.167 minus x here. This is plus x and plus x. So x, and this would be 0.167 plus x. Wow, so we have both of them in our equilibrium. So we have Ka, H3O plus, and then C2H3O2 minus, sorry, the 3 is hard to read, over HC2H3O2, and we would plug all of these in and solve, and our Ka was 1.8 times 10 to the minus 5, and we would solve for x. And we'll finish this next time. But you can't just put in acetic acid and have 0 for acetate. Because they're conjugate acid-base pairs, we have both of them present, so they both factor in. So we write this Ka because that's the strongest acid. We have to start in the initial column. There's going to be concentration in each one of these. And lastly, we have our key takeaways from this. So we've done neutralization reactions where we have weak acid, strong base. They have to be treated as stoichiometric. They go completely to products. We didn't show it, but the same would be true if we reacted strong acid with a weak base. The pH of the solution is dictated by whatever the strongest acid or base is left, and sometimes what's left is both an acid conjugate, or is the acid conjugate base pair, or the base conjugate acid pair. It doesn't really matter. In that case, you have to do an equilibrium with both of them in order to figure out the pH. And you're going to find that that's going to be somewhat useful. So that's kind of foreshadowing for the future. So until next time.